Hello, everyone. Welcome to today's Distinguished Warrior Seminar. This is the last lecture, but definitely not the least of this lecture series. And it's my great honor to introduce today's speaker, Dr. Susan Brantley. So Susan is currently Evan Powell University professor and Mary Barnes, a professor of geosciences at Pennsylvania State University. She is a very pronounced geochemist. Her research is about what controls the chemistry of natural water and how water interacts with rocks, soil, and sediment. She is a member of National Academy of Sciences and American Academy of Arts and Science. She has received many prestigious awards, and in addition to all her very distinguished academic achievements, she is a proud mom of a recent PhD recipient of the Department of Earth and Environmental Sciences at the University of Minnesota. And today she's going to talk about how fracking affects our water. So without further ado, Susan, the floor is yours.
Thank you very much. I had a very short time to get to know your department, and I've been very impressed. I was here once before to give a talk in the Earth Sciences program, and now seeing your engineering program, it's really remarkable how many really excellent researchers that you have here. And thank you, Judy, for bringing me here. So I'm going to tell you what I mean by the critical zone, but what I'm going to try to do in this talk is I'm a geochemist. I work on water rock interaction. I'm going to talk about that in terms of fracking, but also in the context of a societal problem and how we can deal with that. So just to put it in context, I'm sure you all know this, but in the USA, there are about 1 million operating oil and gas wells, but there are as many as 4 million abandoned oil and gas wells. And in Pennsylvania, almost 1,000 are abandoned yearly. And you can see some of them in the woods of Pennsylvania, some beautiful areas of Pennsylvania where you'll come upon an oil and gas well. And what I want to do is think about mostly in terms of water quality issues related to these oil and gas wells. And in particular, I'm going to talk about a new process, in the last several decades, which is, people call it fracking. But when people talk about today's fracking, they usually mean the way we stimulate unconventional oil and gas reservoirs. And so it's a very high pressure, high volume use of water that's pumped down into rocks to frack them open, to fracture them open. But fracking has been occurring since the mid-1900s. So fracking is an old process. We just keep making it better. And we're using very high volumes and very high pressure nowadays to get open reservoirs that we didn't used to be able to get the oil and gas out of, these very tight, low permeability rocks. And this was developed, started in Texas and moved up into Pennsylvania. And you can see some of my information on the slide, which is that we have now reduced our oil and gas imports. We are now a gas and oil exporter. And it's moved the USA away from coal in a big way, which has improved air, climate, and water. And we're now exporting shale gas, which actually has made a big effect in Europe with the Ukraine-Russian war. So the impacts have been huge of this new technique. And I'm not an economist, but I want to frame this up. Jeremy Weber at the University of Pittsburgh, he estimates that almost $3 billion in royalties and associated income have affected Pennsylvania residents in 2017. And a pretty big, or a small percentage of that, but it's still a big amount of money, stays in the county of residence in many of the least wealthy counties in our state. And you can compare it to how much money has been received in unemployment. So these are big dollar amounts that are coming into the state. Now in this map, you can see the gas wells that have been drilled in the Appalachian Basin from West Virginia, Ohio, up into Pennsylvania, and it'll scroll through. The first of these new gas wells was drilled in 2004. And you can see up in Pennsylvania now, we have something 11,000 of these, what I often call shale gas wells, or unconventional gas wells. Unconventional is the type of reservoir. But the build out was very, very fast. So in 10 years, like almost 10,000 wells. And we're the state with the oldest commercial oil well, the Drake well. So you'd think, oh, we're all old hands at it. But most of the oil and gas wells were very old, had been around for a very long time. And now all of a sudden we had this new industry that came in and swept through. And if we were a country, Pennsylvania would be 6th in the world in natural gas production, which is kind of amazing. Well, given that big build out, big and fast and disseminated build out in practically half of our state, there was public pushback. And a lot of it focused on water, and that's what I'm going to be talking about, is water quality. So you can see some of the images of what was happening, and this is more like 10 years ago now. But in reality, like almost 40% of these UOG, that's the unconventional oil or gas wells that were fracked in 2014, were within 2 kilometers of a domestic water well. So people were being impacted, or they were worried about being impacted. And so there's millions of people within this 2 kilometers. And in Pennsylvania, 1/3 of domestic water wells are within 2 kilometers of a fracked well. And that's because a lot of the sort of rural people are living up in the parts of the state that are experiencing this build out. So in these 2004 to 2016, there was thousands of complaints, thousands of spills of wastewater, and there was a lot of pushback. And some very famous people got involved in some of the pushback. So you can see some Mark Ruffalo. One of my images showed Yoko Ono. There was images, this is now from the Western US, where people were getting natural gas methane in their water faucets and they were able to light them. That's not in Pennsylvania, but that has happened in Pennsylvania. And I found it really interesting. I was in Pennsylvania when this is all starting to happen. And, what happened in Pennsylvania, in our little state, actually impacted around the world. And there are bans of fracking around the world. And you can read some of the places where they are, really because of the pushback that happened in the US, but in particular in sort of the Northeast and in our state. So now at the same time this was happening, Rex Tillerson, who at that time was the chief executive of ExxonMobil, made a statement that there's over 1 million wells hydraulically fractured. That's the technical term for this. So a lot of times I'll say fracking, but hydraulically fractured. And there's not one, he said, not one that reported a case of freshwater aquifer being contaminated from fracking, not one. And then Lisa Jackson, who is the EPA administrator under Obama, so chosen by Obama, said at a 2011 congressional hearing that she's not aware of any proven case where the fracking process affected the water. So at the same time that you had this public pushback, you had people that knew a lot that were kind of saying the opposite. Well, one of the problems is that there's a disconnect between the way we use words, so government, industry, and the public, this disconnect. And it's around the use of the word fracking itself. So to an engineer, today's fracking is a specific process, high volume, high pressure, hydraulic fracturing. You can call it HVHF. But to the public, they often use fracking really to mean the whole industry. So everything about, putting the well pad out there, finding the gas, the fracking, getting the gas, disseminating the gas. So they think of it as the whole thing. So that's one of the places of the disconnect. And by the way, I put these 2 SEM images, scanning electron micron images with, I think there's a 500 micron scale bar down, 500 nanometer scale bar down there to emphasize that with shale, which is what we're fracking in Pennsylvania, the pores are nanometer scaled, and that's where the gas is. So that's what we're doing, is trying to fracture the rock so that that gas that has been trapped there for hundreds of millions of years can get out. And what we had been doing before we started doing this HVHF was getting gas out of rocks that were much more permeable, like that sandstone, where you can see the pores, the black, are much larger and they tend to be more connected than in the shale. So what exactly is this? Well, we drill vertical wells, shown over there. And then part of the whole process that developed in the last decades is being able to bend a well into the horizontal part. So you can see the vertical part of the well goes down kilometers, And then the engineers can actually bend the well and then follow a shale out miles. And I think the laterals, as they're called, can go out like 5 miles. And they can, I heard an engineer once say that, he can hit a watermelon, I don't know what, 3 kilometers in the subsurface. So the people, they're really good at this. And so the point is that not only can we get very deep, but now when we hit a reservoir that has a lot of oil and gas, and in this case gas, we can follow that reservoir for quite a ways. And then we have to frack it because that shale is so impermeable and we have to get those pores connected. So the other part of it is that we've been doing this for a long time and we're not creating problems every time we do it. And that's because these wells are not naked holes. They're not, bare rock all the way down. They're cased. And you can see like a expansion image of the casing. They're sort of telescoping. So at the top, there's a 24-inch, casing, and then there's smaller and smaller casings going down. And in some cases, they're cased all the way down and then cased in the lateral as well. And so the argument is that the casings up at the top are what's protecting our drinking water. So what is the actual fracking? Well, along the lateral, there is a casing and they segment it, and working from the end backwards, they actually perforate the casing with like bullets, you can think of them. So they get like dime-sized holes in that casing. And then once they've perforated all the lateral at the top, they stimulate the well, frack the well, and they pump down very high pressure, huge volumes of water that then cause cracking because the water goes out these pinholes or these dime-sized holes and frack the rock away. And you can see sort of an artist's rendering of it. And in the water, they have sand so that once the fracture is open, the sand gets pushed out there into the fracture. And then when they open it up at the top and let the water and gas come back out, the fractures are propped open with that sand. And that's what is propping. And then you see these sand boxes at the well pads when they're doing the fracking. You see them moving all over the states. And a lot of it's coming from the St. Petersburg sandstone out here in the Midwest. This is the what they call like the Christmas tree at the top that they use to do the high pressure fracking. Okay, so the amount of water to frack one well is millions of gallons, and they're up as high as 15 million gallons now because they're getting better and better at being able to do this. So back in 2010, it was like 1 million to 4 million gallons. Now it's up to 15 million gallons because they're going out like 5 meters. And that's just a plot from the New York Times from 0 to 20 million gallons from 2012. And you can see how they were increasing the volume. And so they have big impoundments of water. And there are pipelines that they built out to move the water around. And then there's also pipelines for the gas. So this is huge amounts of water, absolutely huge. There's a great paper by Bridget Scanlon in 2020. And the gray shows how much water comes back, which is called produced water. And then the blue shows the actual fracturing use around the country in some of the different reservoirs and some of the different fields. And they're in billions of gallons. So it's just huge amounts of water. And the water that comes back down in Texas is more than the amount of water that's used domestically, like in 2017. So like really, really large volumes. And then, how much water goes down and how much comes back varies by the field. And so where we are, only about 20% of it comes back. Maybe if you wait long enough, maybe if you wait for the lifetime of the well, maybe half of it'll come back, but less or more of the water comes back down in the other reservoirs. Well, it's not just water. They put in a lot of chemical compounds to make the fracturing happen. And you can read some of them here and what they're used for. And many of them are poisons, or some of them are poisons. And that was really one of the parts that the public really focused on, because they're drinking water and they know they're getting it from the ground. And then somebody else is pumping down huge volumes of water with poisons in it. And they were rightfully worried. The amount of these chemical compounds is very, very small. But in Pennsylvania and a lot of the other states, not all the chemicals need to be reported. Some of them can be proprietary. And there was a lot of fighting about that. Now that has changed over the years. More and more companies now are reporting, but they don't always have to report every chemical if it's a proprietary. And at least 17, I mean, there's been like thousands of chemicals used. They try everything. They call them cocktails sometimes. And at least 17 compounds that are used relatively commonly have been associated with cancers and leukemia. So people were worried about this. And there is a site now called Frack Focus where you can go online and see what chemicals are being used, except for the proprietary chemicals. Okay, so as I said, about half the fluid returns during the lifetime of the well. At least that's the estimate by Terry Engelder. And why do we not know? Why do we have to estimate? Well, because these are so new that we don't know what the lifetime is going to be, and we don't know how much is going to come back. But as the gas comes up, here's an operating well pad. This one company likes to give them real He-Man sounding names. So this is the Iron Man well pad south of Pittsburgh. And these are the wellheads. And as the gas comes up, it always brings up water with it. And it's salty water, and it can be extremely salty. I'll show you some data in the next slide. But the gas and the water has to be separated. And so on every well pad, you'll see these big bins where the salty water is stored. Okay, so all the water that comes up around the country is salty. Every reservoir is a little different. The Marcellus shale, which has been the main target in Pennsylvania in the northern Appalachian, has, I think, the second saltiest brine coming up. And you can see that they're very high concentrations, something like 7 times saltier than seawater. And there's also organics that are present, some of which probably came out of the shale, some of which actually were in the fracking fluid that was used to stimulate. And then there's also radioactive elements. And I think the Marcellus brine is the most radioactive brine around the country. Radium is the main contributor of radioactivity, but at much lower concentrations than the salt, much, much lower, orders of magnitude. So this is what Pennsylvanians were asking: will fracking affect my drinking water? And this was a valid question, and this is why they were pushing it back. And Judy wanted me to talk a little bit about my personal background. So I just thought I'd put this into a little bit of context of myself. I got my bachelor's degree in chemistry, and then I went on to a PhD in geosciences. And then I went on to develop this branch of science, which geoscientists call critical zone science, where what we tried to do is say, well, you can't just look at one little thing in isolation and understand, the answer to your question. You have to put it all together. So we defined the critical zone as everything from the outer edge of the canopy of vegetation down to groundwater. And we said, if we're going to understand processes like what I was interested in was weathering, how rocks weather and react with rainwater and snow water, et cetera. If you're going to understand that, you can't just look at it in isolation. You have to look at the critical zone as one thing, from the vegetation top down to the bottom. So really, I went from sort of my chemistry background, where I actually wrote a paper that was sort of at a molecular scale really early on, and then looking all the way up to the scale of putting it all together in what we call a critical zone. And so to me, this question that I started hearing about from Pennsylvania residents in the early 2000s was, how will this unconventional oil and gas development impact the critical zone? And trying to put the whole big picture together. So in a way, that's a theme in this talk, because if we reduce it to one simple question, we won't see the big picture. And that's what I'm going to try to give you if I get through. I do want to point out, this is an example of what people call a messy or a wicked problem. Many different stakeholders, should we frack, should we not frack? And there's no simple answers. And I think that is a piece of what comes out if you look at the big picture. Okay, so I was looking around in 2010 saying to myself, how can I help my state understand this? People were asking me, is fracking bad? And I didn't know, because it was this new thing, new type of fracking. So I said, how can I help? And I talked to some people, and they said to me, one of the problems is you can't get your hand on data to look at the water chemistry to really put it all together. So I wrote a proposal to NSF, and I said, we will compile data, and not just data from the oil companies, and not just data from academics, and not just data from the government, but also from watershed groups, and we'll convene them together, and we'll look at the data, and think about it, and maybe that'll help the problem. I think at the time I thought, well, we could maybe solve the problem, but now I know we never solve anything, but we can help. So that's what we've done ever since. These are the number of data values up to 2.5 million out to 2022. You can see the sites. We did focus on Pennsylvania, but we put more than that in early on. We have like 30,000 sites in Pennsylvania, many data values, and it's gotten so big, and I'm not a great data manager, that one of my postdocs, Tao Wen, is now an assistant professor at Syracuse, and he's managing the data and doing much better things with it than I can do. Excuse me. So the other point from this slide I want to make is most of our data do not come from watershed groups. We did work with watershed groups, especially in the beginning. Most of our data are data that the oil and gas company, water samples the oil and gas company collected and then gave to, certified analytical chemistry labs. And then the data were given to the state. And the reason they do that is to protect themselves from liability. They go out and sample before they've drilled, and then they give the data to the state. And then if somebody says, hey, you messed up my water well, then they can go to the state and say, no, we didn't look at their water well. It had natural gas in it beforehand, which is, very common. Like 25% of the water wells in Pennsylvania have natural gas in them, regardless of what you're doing, because natural gas is produced naturally as well. So most of our data come from those kinds of data sets. Well, part of Shale Network was that's what we call ourselves. We ran annual workshops, field trips, snapshot days, where we went out and sampled watersheds. This is a field trip where we showed them what a spill would do. This is just a dye, so this is a demonstration. We worked with Trout Unlimited, and that's one of my grad students there. And they we thought we were teaching them, but they also taught us. So they helped us sample. They led us to unplugged or improperly plugged old wells. There's one right there. And if this works, you can see that the bubbling. That's Tao Wen, who's now in charge of the data set. They increased our spatial and temporal coverage for the data, because another theme in this talk is to really understand what happens at a problem. You have to do a case study and really years of work. But then to answer the question of how common are these problems, you have to have the spatial and then temporal coverage. And so they helped us get some of that. They increased our knowledge of the landscape, and they got us started on some case studies where we actually could look at some problem sites and figure out what went on. So now I'm going to really go fast and try to tell you about some of the types of problems that we'll discuss. I put this in here. That's my husband and me, because Pennsylvania is a beautiful state, and I'm going to tell you some of the bad things that have happened, but it's also beautiful. All right, so the most common problem is emission of natural gas into the water. It's the most commonly reported problem. It was, some of what was really was a big pushback. Dimock, Pennsylvania, in the northeastern part of the state, became almost a type locality for this particular problem. And this was one of the papers that was published early on. A sociologist told me this was a signaling event because this got, the scientists up in arms. This shows methane concentration. Methane is the most abundant compound in natural gas. And methane concentration up to 70 parts per million, which is like super high, well above the solubility. And then the distance to the nearest gas well. And so what they were saying was that for their 60 samples, that the closer you got to the natural gas well in this northeastern part of Pennsylvania, the more methane was in the drinking water. And that's obviously, pointing to some real problems. Well, not that long after that, Don Siegel, who's a geochemist at Syracuse University, he was a consultant with Chesapeake Oil and Gas, and that was one of the big companies. He was given access to 11,000 data points. So he made the same kind of plot, dissolved methane, distance to nearest oil and gas well. And the point of this, he said there was no correlation. And so the argument that people made was that first slide I showed you was around a problem site. There was a problem. There was a company that was doing some things wrong with their wells. maybe they weren't doing them wrong. Maybe they just hadn't learned to do it right. I don't know, but they were doing it, and that was in the Dimick area. And so, that was, and then, the other point about this is that, as I've already mentioned, like almost a quarter of the private drinking water wells in the state already have natural gas in them, because there's so many opportunities for biogenic natural gas to get into water, and then also thermogenic natural gas can actually move up into aquifers as well. Well, we wanted to understand the problem, and so the way I thought about it was like, if you get too big of a data set, if there's not that many problems, you get too big of a data set, you won't see them. And then if you get too small of a data set, all you're really doing is saying, in this one site, there's one problem. So, how can you look at the right size data set? And so we started working with Jessie Lee, who is a assistant professor in the computer science program. And she developed this technique because she was in data mining, where she created a sliding window that would move across a map. And it was a 5 kilometer by 5 kilometer window across an area in 200-meter increments. And then these are water samples here. And so in each of the boxes, she would calculate, does that water sample show increasing methane? What is the correlation between that and the distance to the natural gas wells in that box? And then we would basically aggregate or average those correlations in each of the boxes and color code it so that you could then make a map that showed you in what areas you were seeing natural gas increase in concentration closer to gas wells. And so here's just what we were doing back in, I think that was in 2012 or something, I can't remember, but anyway, here shows you the water samples in purple, the unconventional oil and gas wells in black, and this is in right around Dimick. And so it does show you that you see this, enhanced correlation right around the place where Cabot was having some problems with, multiple wells. I think there was multiple oil and gas wells. So it basically found Dimick as long as you had enough water samples in the area. So we started using this to look around the state and try to understand what was going on. We focused quite a bit up in the Northeast because that's one of the hot spots for drilling. And then also we've just started doing work in the Southwest, which is also a hot spot for drilling. And this is where Pittsburgh is. So this sliding window, I should say that the way we've colorized this, we only think of the very highest, the black, as being where we think there could be problems, where there are some oil and gas wells that may actually have caused some leakage into water wells. And so we were always really conservative about how we estimate the numbers of gas wells that we think are leaking. But at any rate, what we observed is in the Southwest, it's something like 0.13% of the oil and gas wells look like they're leaking, and up in the Northeast, it's more like 0.5%. And from this, we could then also go into the state data sets and try to figure out what was going wrong. And we can't prove what's going wrong, so this is all statistical. But up in the Northeast, what we found was that they were casing the top and they were casing the bottom. They were leaving it an open hole in the intermediate depths. And whenever we saw the wells crossing these big fractures, big faults that are up there, that seemed to be where gas was getting in, not from the Marcellus, but from shallower reservoirs. So down here, most of the intermediate depth gas had already been extracted because there was so much oil and gas extraction in that part of the state. But we did see that there were places where the wells mined out coal seams, and some of the coal that had been left still had methane in it, apparently, because it seemed like methane was getting out into some of those as well. All right, but remember, the gas companies were arguing that a lot of the methane in the water was already there. How do you know whether it's new methane or old methane? So new methane being related to the oil and gas. So we started thinking about that, and I worked with Josh Woda, one of my grad students, and with the USGS. And the USGS actually discovered that there was a stream called Sugar Run in Lycoming County in the middle of the state, where it looked like there was gas coming out that was related to some oil and gas wells. And it was the incident occurred at the site where the depth of the Marcellus was the most shallow of any of the gas wells that were drilled. It's only about 1 kilometer. And you can actually see discharge coming up, and it looks like acid mine drainage, but it's not. So we called it gas leak drainage, and it's very high in methane. And what Josh Woda was able to show and published on was, somewhere there's a gas well that's leaking. And as that methane moves through an aquifer, microorganisms can couple oxidation of the methane to sulfate reduction and metal reduction, iron and manganese reduction. And so over time, as this plume moves through, you actually see the water chemistry change, we think. And what we saw, you can follow the different lines there. You can see methane in the black goes up. This is versus time, concentration versus time. Methane goes up until it kind of reaches some kind of steady state. And then the first thing that happens, you get a spike of iron and manganese. And then you see finally your sulfate disappears and goes to H2S. And so there's sort of a chemical signature that moves through the system. And we were actually able to, we've seen it move to the farm fields, beyond it after this publication. And so what we argued was that if you look at iron sulfate, that redox change, those chemistry changes that happen can actually show you that it's relatively new methane. And we use that along with looking at salt content, and I'm not going to talk about that, and then Tao developed a machine learning technique where we could look at, I forget what it was, like 15 different analytes, and then search the data to say, what is the likelihood that the methane is anomalous methane, which would be fugitive methane, maybe new methane. And these are just histograms, the number of samples, and then the percent likelihood that it's anomalous methane based on looking at all these different analytes. And in Pennsylvania, for the data set that we had at the time, we saw like 1.4% of the time that there was methane in the data looked like it was this anomalous methane. We then could get some Colorado data, and we could only see about 0.9%, so much lower frequency. And then in Texas, less than 0.1%. So it looks like in Pennsylvania, there was more problems. Indeed, I think it probably had to do with the fact that we have a lot of natural gas in the intermediate depths, and often in the beginning, those depths were not being cased. Okay, second type. What about direct contamination of chemicals used going through subsurface pathways? Well, this is rare. And the oil and gas industry will argue that it's rare because this is depth in thousands of feet. This is from a SPE publication. Here's the fracture depth around the lateral, and up there is where the drinking water comes. The argument is, there's a lot of intact rock in between that is safeguarding our drinking water. And just look at the time here to see how fast I should go. Okay, so there are different ways that those chemicals can get back up, but to get your hands on data and really look at this is almost impossible, because once a problem happens, it gets litigated and the data doesn't come out. But I think out of zone fracturing, where this fracture went all the way to the top, maybe that happened in that one case where we had a really, a shallow well in Lycoming County. But I don't know. Cementation problems, that has happened in various places. Very small distances between the water and production, that seems to maybe have happened in a couple of places. Blowouts definitely happen sometimes and bring the chemicals back up. Communication with older wells seems to have happened in a couple of places. Early on, we were brought this site by some consultants, and this is a site where someone's drinking water had a chemical in it. And I've been told by the company, oh no, there was no chemical there. And I can say, you can see it in that picture. That white foam was this chemical. It was a surfactant agent. And so we were able to work with the consultants and with the homeowners to try to figure out what happened. And to make it just cut to the chase, there were 5 gas wells. They're all labeled wells 1, 2, 3, 4, and 5 right there. 5 gas wells. The water, the drinking water was 3 kilometers away. Paradise Road water wells, you can see it there. And this was another case where there was a big fault. And what we think was happening was gas and that compound, which is 2-butoxyethanol, were moved not only along the fault in this direction, but then moved up dip along bedding planes and got to the water wells that far away. And the only reason we could figure this out was that the data were released. It was all litigated, but the homeowners insisted the data go public. This is dissolved methane versus time. I'm not going to tell you all about this. Is when the different wells were drilled, when they were fracked, and then what was observed. By looking at the history, we were able to figure out that chemical, which is often called 2-BE, was either in the frack fluid, because one of the wells was fracked, or sometimes it's used while you're drilling. It could have been in the drilling fluid, or apparently it's also used in cement. And when they tried to solve the leaking, they pumped down huge volumes of cement. So there could have been 2-BE in the cement. But regardless, it moved in the subsurface 3 kilometers into the people's water wells. Now, those are really uncommon. And I think our paper is one of the only ones that showed how it actually worked. What is common is spills and leaks of all this wastewater that's coming up to the surface. And this is very common. And most all the spills are small, contained. They don't get into our water. But there are some huge spills. This is a big one in North Dakota. You can read some of the other ones that have been around the country. There was one, I think, in Pennsylvania. It was like 6 million gallons. A lot of really good work is being done by the USGS on these spills, Isabella Casarelli. And they sometimes have seen impacts many kilometers downstream from these huge spills. So why is this a problem? Well, because we have so much brine coming up and we have to get rid of it. This really is, in some ways, the Achilles heel of this whole thing, because so much water is coming out that has to be disposed of. And this is what is done with it in various states and in our state. Sort of state of the art is deep injection into disposal wells. And Pennsylvania didn't have very many disposal wells, so we were trucking ours to Ohio, which was extremely popular in Pennsylvania, but not so much in Ohio. And we now have some injection wells, but we pioneered using the brine to refract or to frack wells. And so that's a good thing, because then most of it stays back down there. But as you've probably heard, around some of these injection wells, enough volume is pumped down there at a fast enough rate that earthquakes are caused. And so that has created some pushback as well. Well, if you look at this is like the number of wells and the number of fracked wells and then the number of spills in black. The spills kind of track the activity, because let's face it, it's coming up, it's got to be moved around, and then it's got to be injected somewhere. And I mean, I think most of you are engineers, if we do anything, there's going to be some problems, right? And so initially in Pennsylvania, the brines were actually disposed into rivers, and the EPA put a stop to this in 2011 because you could see it in the water. And then a lot of it was being impounded for periods of time early on, but this was also stopped because there were problems with that. And we started looking in the surface water chemistry to see if we could see this happening in Pennsylvania. But, there was, in that period of time, there had only been like 76 large spills, and less than 2% were recorded in the data that we could get our hands on. So, I mean, the long and the short of it is there was less than 200 of 70,000 stream kilometers in the Pennsylvania Marcellus that were contaminated in 10 years when 10,000 gas wells were drilled. So why is that? It's because they're not commonly detected in the surface waters. Why the spill frequency is low? I mean, there's a lot of them, but it's low over the spatial area and the time. Spills are mostly small and contained. Most of them are diluted. It rains a lot in Pennsylvania. They can't be distinguished from background often, right? Most of the stuff in this is sodium chloride. Monitoring is sparse, and it's always going to be sparse. And then most entities don't share data. So you can't find it, in the data. Well, right about this time, some economists at the Booth School of Economics and University of Chicago, much to my chagrin, took the data set that we had in Pennsylvania, but also from the state, and used this, what was to me a new technique, fixed effect analysis, and were able to look at the surface water chemistry across the whole country, and they were able to show ever so slight increases of salt concentrations in the surface water that correlated with the shale gas wells. And I was lucky enough, in my opinion, to review the paper, and I went back and forth with them because I just couldn't believe they were finding this in our data set. But but it's real. But they use this new technique that I didn't, and then they taught us about. And I think it's real, but ever so slight. So really small increases that correlate with the shale gas wells. So they actually came to one of our workshops. Normally they go to like Davos, but they came to Central Pennsylvania to one of our workshops, and they taught us how to do this technique. So my grad student, Sam Shaheen, who's from Minnesota, he's looked in the groundwater data sets to see if we can see an increase in concentration of salts that correlates with the shale gas wells. And I just go real fast through this. This is the medium barium and medium strontium. I didn't emphasize barium and strontium are sort of signature elements that you can see. And the median of the data, these are box and whisker plots, correlate with UOG wells. And so that you see the median barium is higher within a kilometer of a UOG well than it is further away. If you then look at your correlation with respect to the spills, which are, the state has pretty good data sets for, you see an even stronger statistically significant correlation. So it looks like we don't see statistical correlation with casing or cementing violations. So I don't think the salt is getting into the groundwater from, underground. It looks like it's correlating with the spills. So you can use that fixed effect analysis and actually calculate an increase in concentration per UOG well within a 1 kilometer radius. And you can see that very, very tiny micrograms per liter concentration increases in the barium and strontium correlating with wells within a kilometer. And when we look at the barium to strontium ratio, it's like 0.94 in that statistical analysis. That's getting pretty close to the barium to strontium ratio in the produced waters. So it makes sense from that point of view. And it's stronger for the spills than it is just for the, per UOG well in the radius. So we thought about this more. You could do a mass balance calculation. If you have a spill more than 250 gallons and you make some kind of generic ideas of how much salt you'd need to be able to detect it, you can convince yourself that, a big spill could cause this groundwater effect. And indeed, the medium barium in the state is 23% higher in the groundwater within a kilometer of a 250 gallon spill. And the red squares are the spills. And it's even stronger if you look at the bigger spills, the greater than 500 gallon spills. We also looked at some of these impoundments that early on were being used to impound some of this water. And there's some famous impoundments. The Jaeger impoundment is one of them. The Carter impoundment is one of them. There was a book written about it called one of these, Amity and Prosperity. It was a Pulitzer Prize winning book. And there was about 8 impoundments early on that there seemed to be problems around. And we can see that the median barium is 34% higher within a kilometer of some of these problematic impoundments. And that's why they stopped this, not because of our data set, because we've only just identified this, but because downstream of some of these, very close by, they were having some problems. We also started using machine learning based separation of sources of chloride. So chloride can come from road salt and homeowners. So we used a non-negative matrix factorization where we look at a matrix of the chemistry data, and then we use this technique that's called a blind source attribution. So we don't assume that we know the different end members, but we can pick it out with this technique called NMF. And then what we end up seeing is that in the groundwater, we do see evidence, we think, for road salt. We do see evidence for chloride from rainfall, but we also see evidence for chloride from the brines as well. And so we did that sliding window technique, and we've identified some spots where the chloride that NMF tells us is coming from the brine increases with the density of UOG wells. We've compared these kind of results to groundwater models. Jim Sayers out of Yale is doing some forward models showing where he thinks leakage or spills could get into groundwater. And so, where we see problems maps to some extent with what Jim Sayers has predicted from his hydrologic modeling. One of our 3 chloride hotspots where it suggests a health risk, and I haven't told you that, but I'm going to show you in a second, is very near one of those impoundments. So we really think that these hotspots are real. We're trying to get money now to go back out and sample around them more to get more data nearby. But we can also look at the question of, if it is produced water that's producing this chloride, we can ask, like, what is the ratio of, some of the metals that are health problems? What are the ratio to the chloride? And then if we calculate how much chloride increase there is per UOG well within one of these hotspots, we can ask the question, where might there be some human health risks? And it turns out that thallium, according to this calculation, would exceed the EPA maximum contamination level for human ingestion in 3 of the 5 hotspots. And then arsenic, beryllium, and cadmium get within 75%. So we think that if water quality is a human health risk, if it's a culprit, this would probably be why from some of these very low concentration metals. And indeed, thallium ingestion is associated with low birth weights. And there have been some health studies now that have shown that infants born within a mile of one or more of these wells during the production phase are 20 to 40 grams smaller at birth. This just came out in 2023. And they also concluded that children within a mile have a very slight chance of a higher incidence of lymphoma, extremely low rates, but statistically anyway. So it is possible that some of this could be a health risk, water quality, but you also have to remember there are also lots of studies that have shown hazardous air pollutants that have been released that would be in what people are breathing. So correlation doesn't prove anything at all. All right, so this is what I tried to show you. I think UOGD does affect our water, but it's at an extremely small fraction of shale gas wells, and it's mostly from spills. And it's mostly this brine that we need to be worried about. Fracking itself only very rarely affects water supplies, highly unusual accidents, but we're disposing trillions of gallons a year of wastewater nationally, and it really does impact the water in spills and impoundment leaks. Water data is very sparse. Incident data are rarely accessible. And to understand the actual cause takes usually years of work, a lot of time, and a lot of money. To quantify frequency, you're really looking for rare events in a disseminated industry. It's a very unusual industry. It's a huge industry, but it's disseminated. And so you have to sort out the data from the background, the incidents from the background. Also, yay, geology matters. More problems where the water residence times are shorter. Pete McMahon at the USGS was the one that started to show this. I mean, it kind of makes sense. But even if the incidents are rare, even if the problems in the water are rare, homeowners' well waters in some places are localized, severely impacted, and people, their lives are really impacted. And we've been working with some geographers at Penn State, Jen Baca and her student Owen Harrington, and they've been talking to Pennsylvanians about what they're worried about, and this is what they're worried about. And we're trying to get money to go back, especially around Pittsburgh, that southwest part of the state, to look at the hotspot areas that we've identified in that thallium question that I mentioned. But this talk focused on water quality, and this is where this critical zone idea, where you got to think about the big picture. I didn't emphasize that digging up ancient carbon, leaking it, or burning it and releasing CO2 into the atmosphere and changing the climate. I didn't even talk about that. So I kind of just want to leave you with this thought that, you know, I think reasonable people can disagree about whether fracking has been good or bad for the US from a sort of a water quality point of view. But I think that we should agree that really we need transparency so that we can figure this out. This was the data that I showed from one site. This homeowner litigated, and then when they settled, they insisted the data go public. That's the only site that I know of like that in Pennsylvania. And that's why we could figure out that one site, what was going on. We'll figure out what we think was going on. So I don't understand why we can't make groundwater data more transparent. You know, think of the black boxes on the airplanes, you know, where they figure out what happened no matter what. I think we need to pull CO2 out of the atmosphere, and we need to figure out how to do that. And I'm very big on this idea that, you know, we have to do yes in my backyard instead of no in my backyard. Because if you are against fracking, and I meet a lot of people that are against fracking, then you have to be in favor of something, because you are using energy, of course. And so you have to be in favor of nuclear, which a lot of people that are against fracking are against nuclear. If you're not for nuclear, then how about geothermal, solar farms, wind farms, critical minerals for, you know, batteries, all that sort of thing. And that impacts the landscape, much more of the landscape. The footprint of these shale gas wells is actually really small when you compare to how much energy is produced. Most of the well pads have, you know, nowadays have like 5 to 10 wells on the same well pad. So we're going to have to embrace something. And I tried to kind of give you a nuanced view of this. And I just want to point out, I was funded all the way through this by National Science Foundation, Penn State. There was a gift to Penn State from General Electric that was given to me with no strings attached. And right now we're funded by the Health Effects Institute. So thank you for your time.
Thank you, Susan, for the great and extremely informative talk. So we have time for a couple of questions. Anyone? Okay, maybe I will start. Okay, yeah, Raphael.
Nice talk. Thank you very much. I have a question about the method that you did with the weighting on the area with the
sliding window.
The sliding window. Did you? I imagine that you did some tests on like optimizing the size of 5 kilometers by 5 kilometers and increasing 200 by 200 meters. Do you know if there is some kind of possibility of an adaptive window, like for regions that you have more information, having a smaller area to calculate that?
Yeah, that's a great question. So what you're emphasizing is, you know, some of the windows have a lot of water samples and some of them don't. And so if you could have an adaptive window, whether that would be a better approach, I think that's a great idea. We did change the size of the window to try to get a size that would have enough water quality samples in it, and we get, you know, good statistics so that we could see the correlations. But we didn't think of an adaptive window. We haven't worked with that. I think there's a lot more to be done with this kind of approach, and, you know, to look at those kinds of things, because you are looking at, you know, a spatial problem, and how to get the data out of that is not, or the signal out of that is not really clear. But that's a great idea.
Any final questions? Okay, maybe I ask. Oh, okay, there's an online question.
I thought you had a question, Molly.
Okay, our question from online says, has your work gotten any attention from policymakers, and do you see any regulations changing because of it?
Yeah, policymakers are interested. Now, I'm not so bold as to say that we've, you know, changed the policy, but we're showing some of the same things that the state government has found, like the intermediate depth casing. Now in Pennsylvania, they have to use intermediate casing to case off the well, where there's gas in the intermediate depths. That's not because of us. The state kind of came to that, and they had to go back in and remediate some of those wells that way, put the casing in afterwards. One of the big things that's being fought out right now is what is the setback distance? So how far away from somebody's home or water well do you have to be to drill your well? And right now, I think it's like 500 feet or something like that. And there's a big argument going on where people are arguing it should be at least 2,500 feet. And I would argue strenuously that it should be longer than it is right now. But it's a political decision, right? It's like what I try to do is show what the data shows, and then people have to decide what risk they're willing to tolerate. And how do we decide that? By politics, like everybody's like hates politics, but that's how we decide these things, right? And so the governor, I think, would like to increase the setback distance. At least he said that when he was campaigning. And but the industry is pushing back on it. So they're fighting it out in the legislature right now.
Okay, last question.
Hey, thank you so much for the talk. I was just curious, with a lot of your like images that showed the depths of the shale and like the water tables, like where the water lies that people are getting their drinking water from, it seemed like there was you showed like a big separation between the two. And how sure can you be about that like the water, like aquifers or like where people are getting the water isn't fed by someplace that's close to the shale? I guess.
Yeah, I think the figure you're talking about was one that I showed that was from the publication of Society of Petroleum Engineering. And they love that figure because it really emphasizes in your head how much distance there is. Well, so to answer your exact question, they can geophysically from the surface interpret how long the fracks are, what depth they reach up to. And so from that point of view, I think we know quite a bit. Now, do they know where every fracture in the surface is or fault is in the surface? Not really. And so, does that frac intersect a fault which can actually move fluid, in actually, open enough that it can move in sort of your lifetime or something like that? That I don't think we do know. So does that answer your question? But I mean, in general, like hundreds of meters at the surface versus kilometers, as long as they're fracking at really deep depths, those fracks shouldn't get up here, at least not very often, but we can't prove it, and geology matters.
Thank you.
All right, let's thank Dr. Susan Brantley again for the great talk.
Thank you, Drew.